today's lecture, we'll discuss about difference between BJT and FET. The physical and circuit diagram of BJT and FET is shown. The three terminals of BJT transistors are named emitter, base, and collector. Each terminal is connected. The emitter and collector are both heavily doped, with the emitter comparatively heavily doped than the collector. The three terminals of FET are drain, gate, and source. Based on its construction, FET is available in two types, that is N-channel FET or P-channel FET. BJT is a current-controlled device that uses two junctions between P-type and N-type semiconductor material to amplify or switch electrical signals. While FET is a voltage-controlled device that uses a metal gate separated from the semiconductor channel by a thin insulating layer to control the flow of current. In BJT, the base emitter junction is forward biased, allowing a small current to flow from the emitter to the base. This current controls a larger current flowing from the collector to the emitter. The current amplification is achieved by the gain of the transistor, which is the ratio of the collector current to the base current. In FET, the gate voltage creates an electric field that attracts or repels the charge carriers in the channel, forming a conductive path between the source and drain terminals. The current flow is controlled by the voltage applied to the gate, and the resistance of the channel is controlled by the width of the depletion region. In FET, the gate voltage creates an electric field that attracts or repels the charge carriers in the channel, forming a conductive path between the source and drain terminals. The current flow is controlled by the voltage applied to the gate, and the resistance of the channel is controlled by the width of the depletion region. BJT is commonly used in analog circuits such as amplifiers, oscillators, and switches, while FET is commonly used in digital circuits such as logic gates, memory cells, and microprocessors. They have higher gain and bandwidth than FETs and are well suited for low-frequency applications, while they have low power consumption, high input impedance, and fast switching speed, making them ideal for high-frequency applications.